Hello, welcome to my presentation on building applications securely. My name is Eoin Woods. I work for a company called Endava. We build a lot of software for other people. There's about 8,000 of us now. I've been there for 6 years. I'm based in the London office, but we have people in many countries across the world. And before Endava, I've been doing software quite a long time. I spent about 10 years building software products. That's where I got interested in security. And then I moved into capital markets, people like big banks, and they're also pretty interested in security. So I've done quite a bit of it over the years. But I've always been a software engineer. I started as a software engineer and became an architect, and now I'm a CTO. But I've always been dabbling in security. And in recent years, I've become more and more concerned about the threats our systems are facing. And so I've become more and more interested in telling people about software security. This talk doesn't really exist in isolation, so I'll just mention the others very quickly. I did an original talk some years ago called Security Beyond the Libraries, because I was a little bit maddened that people kept equating software security with bits of technology. And that was well received. And then I did a couple of others, one on the OWASP top 10 web security threats, and one on how you design systems by using security principles. And that all led me really to this talk, which is the one I'm going to give you today, which is a little bit more nuts and bolts. It's a bit more about, if you're in a development team, how to improve your software security day to day. But if you want a little bit of a broader context, those other talks are out there, and I'm sure you can find them with a web search or via my website. We're going to talk about a couple of things. We're first going to talk about the threat. The threat's important because that's the motivation for doing good software security. We're then going to explain what I mean by software security and why that helps to mitigate the security threats that our systems face today. We're then going to talk about some specific principles that I hope could guide your work when you get back to work after the conference and start thinking about how might I improve software security in my project. And then there's some quite specific sets of guidelines out there. I just want to talk through some of those. I can't cover all of them. I can't cover them in depth, but I hope to put them in context and maybe give you a few practical tips on where to start when you start thinking about specific implementation guidelines. And like any good talk, we'll finish with a summary. So, the threat. What do I mean by the threat? Threat's a word that's used very commonly in software security and security in general. What we mean is that we need systems that are dependable, even when things go wrong. The three great security terms are malice, mistakes, and mischance, or as I prefer to call them, some people are bad, some people are careless, and some people are just unlucky. And the interesting thing about security is it's important to remember it's just as much about preventing problems when people are careless or unlucky as simply guarding against the bad guys. And we often focus on the bad guys, but actually security is useful beyond that. It protects us from ourselves some of the time. Software security, IT security in general, aims to mitigate all of these situations. And if you look today at the threat landscape, so we talk about the threats to our systems, if you look at the threat landscape we have today, it's reasonably serious. This is a snapshot actually from several months ago. This is the Kaspersky's cyber threat real-time map, as they call it. And you can find that on the internet. It's freely available. And a number of other vendors have them as well. They give you a dynamic view of the threats that these big security vendors are seeing unfold in real time on the internet. Honestly, it can be quite a concerning thing to go and look at, but it's quite useful. It's quite illustrative. You can see that security threats are out there the whole time. But really what I worry about with software security in particular is that when we build applications today, we don't always think about it, but they often become a so-called digital channel. That is a system that's not just used internally, but is used to connect to other systems, other people, other organizations, often via the internet, a very public channel. That means that we have to start thinking about security for these applications in a slightly different way. We're also putting a lot of system interfaces on the internet today. How many systems do you consume via an API that's internet connected? So those interfaces are there on the internet for anyone to access unless they're carefully built with security in mind. And of those APIs, years and years ago when I started out, APIs used very proprietary protocols from companies like Hewlett-Packard and IBM. And really, if you didn't have the documentation, it was very hard to use the API. You really had, it was all in binary. You simply had to know how to use it. Today, well, not only are our protocols effectively human readable, think JSON over HTTP, but actually we make them self-documenting using technologies like Swagger or OpenAPI. And that's a marvelous thing. Self-documenting systems are a huge productivity gain. But if somebody wants to attack your system, we're also making it even easier. We're not just giving them an API that they can access and see if they can find vulnerabilities in it. We're actually giving them hints and tips as to where to find the vulnerabilities by making it self-documenting. But the last trend that I'm seeing, everyone's seeing, which is, I think, the most concerning, is how attacks are being weaponized. And by this, I mean, until a few years ago, there were many people in the world that could perform attacks on systems. They were skilled hackers. But actually, it was a fairly fixed, closed community. Some of them were good guys, some of them were bad guys, some of them were in between. But actually, there weren't very many of them in global terms, maybe hundreds. So for one of those people to want to attack you, you had to be a valuable and probably quite high-profile target. What's happened in the last few years is that more and more quite sophisticated attacks are being packaged as software systems or as software utilities and sold, often via the dark web using cryptocurrencies. This means that the reality is that a bored teenager in Lyon in France, from his bedroom, can download a sophisticated attack tool and deploy that to attack your system. So we have to take the kind of threat that used to be seen as rather esoteric much more seriously. And the scale of denial of service attacks, which I'm sure you've read about in the press, so I hope you haven't experienced yourself, that we're seeing today, are a good example of that. People can rent botnets as SaaS services by the hour. You have to admire the entrepreneurial spirit of the people setting them up. But actually, this is really, really serious. It means that somebody with a grudge against some other organization doesn't need huge amounts of computing resources. They don't need huge amounts of skill and ability. They can simply go and rent a potentially deadly botnet to perform a denial of service attack on your system. So there are many factors that we've got to bear in mind when thinking about security, but we do need to focus a little more on it than we used to have to. The reason being is that the threats today are so much more active, widespread, and mechanisms that are potentially hostile to us are much easier to access. You can see this when you actually look at the data. There's a site on the internet called Information is Beautiful, where a data journalist has created many, many visualizations of commonly available data sets. One of his very famous visualizations is that of data breaches. He has obtained a large data set, which keeps being updated regularly, of data breaches. He's then worked out how to visualize it using this circle notation. And back in 2005 to 2007, you can see that things weren't great. These data breaches are normally a case of personal data being stolen. So even back in 2007, TK Maxx had 94 million user records stolen. I think they were credit cards. So that's really quite serious. But you can see that data breaches weren't that common. They were relatively isolated, and maybe not that large. Whereas by 2008, and getting on to 2011, they weren't getting a lot bigger, but you can see there's quite a lot more of them. A lot of them are relatively small. Some of them are very sensitive. That's the UK National Health Service, and that's the US military, both losing significant amounts of data. But it still looks like a manageable situation until we start moving into about 2012, more recently 2015, and you can see the scale of breach is becoming very large. The number of users being affected is huge. The Yahoo breach back in 2012, 2013 was massive and affected a huge number of people, including me as it happens. As you can see from the graphic, the average size is getting rather bigger, and there's a lot less white space, isn't there? The breaches are getting more regular and more serious. Coming up almost to date, it's really now quite a serious situation. There are data breaches happening everywhere, and that's for a number of reasons, two main ones. The first one being, as I mentioned, there's a lot more attractive data is now available via internet connections. And the second thing is our attackers are getting better at this, more sophisticated and more practiced, and then they're managing to break into systems more often. Bringing right up to date, and even people like Microsoft and Facebook are suffering major data breaches. So, you know, I always think when Facebook and Microsoft are suffering data breaches, I probably need to take them quite seriously. One of the temptations, of course, when we see these kind of threats appearing on the internet and data breaches and all these big things happening is for those of us on the application side to go, I think you find that's an infrastructure problem. I'm sure they broke in through a firewall or something. Or it's probably the operating system, probably the network problem, probably nothing to do with us. Actually, often infrastructure is a problem, and there are many vulnerabilities in infrastructure, and frankly, many of those data breaches did have an infrastructure element to them. But actually, when you look at the research, and Verizon are one of the companies that do a lot of research in this kind of area, they do surveys every year to find out what's really going on, how data breaches are really happening, and what the problems are. Actually, when you look at a recent Verizon report, you find that about a quarter of data breaches are actually caused by application software. So, you know, we've got plenty to do as well. So what do we do about it? Software security, I would argue, is one of the key ways that we can mitigate security threats in our software. It's worth just stepping back and saying there's a lot of different parts to security practice. There's the infrastructure stuff I was talking about, both design and deployment. There's how we operate systems securely, so we don't make mistakes in operation, which are insecure. There's how we design applications securely and how we do secure application implementation. We're going to talk about implementation in this talk, but it is important to bear in mind we need to get the other bits right as well. Secure application implementation is all about taking some inputs into the process from the design process, so we know how to design a system securely, but then as we build our application, working out how are we going to build it in such a way that it's got a fair chance of being secure. What are we actually going to do when we're doing implementation in order to achieve security? And how do we check that we actually are going to build and are building a secure system? We're mainly going to focus around what you do in this talk, with a little bit of how you build the secure software development lifecycle. We're not really going to talk about testing and validation. There just isn't enough time. So talking about how you build, how are we going to organize ourselves in our development lifecycle? We normally talk about integrating security into the development lifecycle. We could, of course, just do it ourselves. We could read all the books and work it out. But actually, a lot of clever, experienced people have done a lot of this thinking for us. And there are 4 things I'd just like to introduce you to quickly, which might well be of use to you when you get back to work and you're thinking, how do we improve our security practice? It's the Microsoft Software Secure Development Lifecycle. It's the OWASP SAM lifecycle. There's the Building Security In model, and there's SafeCode, who are an organization it's well worth knowing about. Microsoft have been trying to develop secure software for a long time. It would be fair to say that they've got a pretty impressive security unit now, and most of their software today, they're doing great security work on. For their own use, they developed this secure development lifecycle with a standard set of phases and a standard set of activities. It's very well documented on Microsoft's site, and they give it away freely. It's well worth taking a look at. For those of you from an agile background, it probably does look a little waterfall, and it's worth bearing in mind it was developed by a product company that does follow a fairly linear process to produce regular releases to be shipped out to customers. But these activities are very much the activities you need to integrate in the agile lifecycle, as well as perhaps a more waterfall or sequential lifecycle. It's still the important thing to know about. OWASP are a volunteer-based organization who are very focused on application security. They've come up with a slightly different approach to helping you work out what's important to focus on. They've got a maturity model. They view that there are 4 important aspects of achieving secure software. There's what they call governance, there's the construction aspect, there's verifying what you've built, and there's operating what you've built securely. In each of these areas, they've identified some key activity areas, and they've built a maturity model so that you can use checklists and questionnaires in these different areas to work out where you are at the moment. And then it gives you a framework in which to think about, where do I want to be? And it guides you. It's got lots of suggestions for how to improve your practice in these activity areas. It guides you towards a more secure software delivery lifecycle. It's something that's come very much out of practice. Unlike the Microsoft one, it's used widely. It's very thorough and practical. It's freely available, so it's well worth becoming familiar with. Another thing it's well worth being aware of when you're considering your security practice is the Building Security In maturity model, the BSIMM. It's sponsored by a company called Synopsys, and they've been running it for some years. What they do is that they cooperate very directly with firms who pay them to come in and look at their security practice. And they run questionnaires, and they do interviews, and they overall do an assessment of that company's security practice. They then pool all the data and create a model every year that benchmarks the individual firms against the best and the average and the worst, both in their industries and in the study as a whole. And then, of course, that benchmarking is confidential to that company. The great thing for the rest of us who maybe don't want to or can't join the program is that they publish the genericized statistics freely every year, and they're available from Synopsys. So, for example, this is an example for one particular firm that all the firms in the study averaged out to the green shape. This imaginary firm averaged out to the blue shape. And so you can see that it's stronger than the average in some areas and weaker than the average in others. Well, what we can do is that we can effectively get the green part for free from Synopsys. And then all of the materials for the BSINM are freely available. So you can use them to do a sort of self-assessment and think yourself, where do we need to get stronger? What's important to us? What's not so important to us? And perhaps importantly, how well are other companies benchmarking in these areas so that we set ourselves realistic goals. Finally, SafeCode. SafeCode is a membership-based organization of some of the leading practitioner firms in the software security industry. SafeCode is probably not something you'd be looking to join, at least not initially, unless you've got a very mature security practice. But the great thing about SafeCode is it was set up to improve security practice right across the industry, not just in the member firms. So all of their material is made available freely, and they make guides available freely, they make tutorials available freely, they make training available freely. So go and have a look at it. The most well-known thing that they produce is their fundamental practices guide, which is a very thorough written guide to how to improve secure development practice. But they also, as I say, produce training and tutorials, which are very valuable and freely available. It's a great resource, especially when starting out with software security. So when we go back to our projects, this is all very well, and this is probably all maybe quite strategic stuff you might well want to start thinking about, but how do we just get people thinking more about software security and doing better work relating to software security? What I found is that there's a set of principles that if we can internalize them and use them together as a team, they really help us improve our software security in an incremental and practical way. The first one, which I think is probably the most fundamental one, is that security is everybody's concern. One of the problems historically is that organizations have had security groups or software security groups or security engineering groups. There's always been a tendency in those cases for the application teams to decide that actually security was important, but somebody else was largely going to solve it for them. And nothing could be further from the truth, of course. The security engineering teams can't possibly fix all the problems that the teams have with their security. They can only help them to do it. So we've got to move from it being a feature that people want to bolt on and want to get somebody else to come in and do, to be a concern that everyone on the team is worrying about, hopefully the way that they are, for example, about scalability or performance, because it really needs a team-wide awareness. Otherwise, it's pigeonholed as a specialist's problem, and the specialist can never address it by themselves. And what we're aiming to do is to integrate security awareness into normal development tasks. A second principle is the use of security champions. Let me explain what I mean by that. We can accept that security is everyone's problem. The problem with that tends to be in practice that it's always someone else's problem. Yeah, it's everybody's, but I'm busy. I'm sure that everybody else will get on with it. What you really need is enthusiastic advocates who really want to take ownership of security and drive security awareness in their environments and their teams. These people we term security champions. This is something we do a lot at Endava. We have champions for all kinds of things, and security is one of them. But actually, it's quite a common term in the industry to form a security champions group. These are the security enthusiasts. These are the people who think security is not only important, it's interesting, and they want to learn more about it themselves. So you need these people to be largely self-selecting. Of course, encourage them. Of course, make it beneficial to be one, but they've got to have personal enthusiasm for the subject. Well, once people have volunteered, make sure you invest in them, involve them in the development lifecycle, involve them in security policy, promote them, support them, look after them, and make sure that they feel valued. If you can get a working security champions group, they will work magic across your organization in terms of awareness, in terms of improving security practice, in terms of day-to-day security work. The third principle is to make sure that you focus continually through the life cycle. In what I would term the bad old days, security was something that was thought about very late. Typically, software went right through development and often testing, and then people started to ask questions about, is it secure? How are we going to test it? How do we improve the security? And then the corporate security group would come and look at it and tell you you'd failed all the security tests, just as you thought you'd finished. That was, as I say, I view those as the bad old days. But what we're trying to do now is to integrate security work right through the life cycle. So we're thinking about security requirements early. We're doing good security design work as we're designing the system. Every time we do implementation, we're thinking about the security of our implementation and testing it. And when we're doing our testing work, we make sure we integrate security testing in it. And of course, in most agile life cycles, we're doing these things repeatedly. We're not doing them in siloed stages. We're doing them repeatedly in maybe 2-week iterations to deliver software continually, because you really cannot test security in at the end of the life cycle. That has been proven not to work very well. The other thing is it forms a huge delay at the end of the life cycle, which we want to avoid. We want to get our terrific new features into production quickly. So we need to integrate it right through each life cycle stage. It's worth talking at this point about Devsecops, something that you may be doing, you may have heard of, or maybe it's a new thing, but DevOps has been around for a while now, and this is how we avoid those silos of dev and ops, with their totally different objectives, not getting along very well, and this gap in the middle, which an old colleague of mine memorably named the desert of responsibility, where no one wants to tread. And DevSecOps is about bringing cross-functional teams together who both develop and operate the software. DevSecOps is really the sort of logical extension to that, because a danger you can have if you have dev and ops together is you've still got a security silo, and the security folks won't let anything go live until they've had their say, if you like. So DevSecOps is about integrating security work into the team. Historically, security had often been the team that says no, but then they were often consulted late. They're not very well resourced. They often don't understand the context. They're often not a team that people go and proactively talk to. So often they had to say no. What DevSecOps is all about is not relying on those specialists, we've said, making it everyone's problem, and making us all security engineers thinking about security right through the dev and ops lifecycle, hence making DevSecOps. The next principle is that doing good software design actually improves security. The reason for this is that if design isn't done carefully, you get careless design, that is a very, very common source of vulnerabilities in the software. Things like strong typing, well understood simple mechanisms that are easy to test, well-structured code, all aid security. As Bruce Schneier likes to say, you cannot secure what you do not understand. Good design helps us to keep intellectual control of our software. And the simpler an implementation is, the easier it is to both understand and apply security mechanisms to secure it. To give you an example, this is a simple Java servlet, and it's a perfectly reasonable piece of code. It's a GET request. It pulls a couple of parameters out, it calls a service, and then it renders the result back to the caller. Absolutely fine. Well, nearly fine. It does have a bit of a security problem, or it could have a security problem. What happens when we parse that in and pass it into quantity? Well, kind of nothing really. We just pass it through. What happens if quantity is less than 0? Well, we don't know. Hopefully, the order service rejects it with a well-structured error, nothing goes wrong, but perhaps it causes runaway code. Perhaps it causes a credit instead of a debit in a financial account. Perhaps it causes a serious error in the back office that causes the back office to misbehave. There's all kinds of potential security implications of a negative value not being handled. And I realize this is a fairly trivial example, but it's an example of the kind of thing that a more rigorous approach to design can help with. How about if we introduce strong types and the types had the business rules encoded into them? In other words, how about if we use domain-driven design? If we have types that have business rules built into them, one, this produces better software, it's easier to test, it's more reliable functionally, but it's also very, very often, it has beneficial security side effects. So it's worth us thinking about being intentional in our design in order to improve security, as well as other features such as code coherence and quality. My next principle is to use proven tools and technology. Software is really hard to secure. You see the vulnerabilities that come out of major security-aware vendors all the time. That's fairly obvious. If they're getting it wrong, we're getting it wrong. If we look at the number of vulnerabilities found every week, really, in open source software, it's obvious. These are not people with no knowledge. They're highly skilled software engineers. They've often got good security awareness, but yet they still put vulnerabilities into their software. And security software, the software that is actually implements security mechanisms, it's really hard to secure. I used to build it. I can assure you, it's really, really hard to secure. I used to have sleepless nights before we shipped anything. In reality, you don't tend to find all the vulnerabilities very early. Vulnerabilities emerge over time. And that's why if you go to organizations like NIST, US government security organization, and you look at the vulnerability lists that they produce every week, some of them are for brand new things, but some of those vulnerabilities are for things that have been in the field for a while. And the reason that vulnerabilities emerge over time is because people attack them. Hopefully they're white hat security analysts attacking them, but sometimes they're not. The important thing is that you need some experience with how something is used and possible side effects of using it before you know what the vulnerabilities are. So if you use proven tools and technologies, both in your standard technology, but especially in your security technology, you're likely to reduce the number of vulnerabilities in your operational systems. My next principle is to automate security checking, or at least automate as much security checking as you can. Some security checks can be automated. For example, static analysis tools, dynamic analysis tools. These are very, very useful because they bring consistency and efficiency to part of the security process, which human beings are really bad at. If you ask a human being to read their code and check it for security vulnerabilities, honestly, we're not very good at that as humans. That's why we put the vulnerabilities in to start with. Even if we check someone else's code, these things are subtle. They're quite hard to find, and humans aren't great at it. Whereas software pattern matches, which is what static analysis tools are much better at it. Dynamic analysis tools are ones that perform sort of automated penetration testing and other similar runtime attacks. And again, human beings can do them, and human penetration testing is immensely valuable. But there are many, many routine attacks which we need to check for, which it's much more efficient, consistent, reliable to use a DAS tool. They also allow, you can often apply them very early in the life cycle, right through the life cycle, as we were saying. So you can find some problems much earlier than if you're waiting to build enough of the system to make it worth doing manual penetration testing. There are a couple of challenges with them, though, apart from complexities of buying them and applying them. Many of these tools have a tendency to produce a lot of false positives, especially to a new code base where you haven't yet, if you like, trained the tool for what to look for, or if they're applied to quite old code bases, which already have a lot of vulnerabilities in them. The other problem is that when they produce a lot of perhaps valid vulnerabilities that need to be assessed, if there's a lot of them, it can be hard to know how to work through that list. You've got to prioritize them ruthlessly. You never have time to fix them all immediately. So they do bring a couple of complications into the SDLC, but they definitely have their place. They're not the only thing you need to do, but they're a valuable way of bringing consistency, efficiency, and automation to some processes that human beings aren't very good at. Today, nearly all of us use open source software extensively in our systems. We've done some analysis in Dava for applications we build for clients. Many of them in terms of binary size, when we measure the binaries that we're shipping, such as jar files for the production system, we find that 75% of the code that's actually in operation is open source. It's even higher in some systems. That's all third-party code that we tend to pull from internet-based sources in binary form normally. In fact, we encourage our engineers to use it in binary form because we don't really want them making very localized changes to it. All of that third-party code is a potential security risk. In fact, code you buy is a potential security risk too. The problem with open source is that the link between the producer and the consumer of the code is very weak. With commercial software, there tends to be a much tighter link between the two because of support agreements, so that if vulnerabilities are found, it is reasonable to expect a commercial vendor to proactively notify everyone who's using that software because they know who they are. It's not reasonable to expect an open source project to do that. They don't know who's using their software or what they're using it for. So the responsibility falls much more on us as the consumers of the open source. Quite a number of tools exist for checking for open source security, risk, and compliance. And the four names that I'm familiar with are Black Duck, White Source, Sonatype, and SNCC, SNCC being the newest into that market. What they do is they scan code. They're often looking for libraries. They extract a binary signature to uniquely identify the library. And then they have huge databases running as SaaS services full of information about open source software. And that's all populated mainly by human beings. They have very large teams of analysts work for these companies, constantly staying on top of what vulnerabilities are in which pieces of open source, what operational risk, for example, how many committers these projects have, and checking the licenses that these projects use to license their software. So these tools establish what open source you're using by calculating the signatures for the binaries. They upload all the signatures, and then they get a large reporting return, which you normally view in a graphical dashboard, so that you can see what open source licenses you've got, what vulnerabilities are in the software, and also an assessment of possible operational risks using the open source, all of which is very, very, very valuable for improving application security. And most of these tools can be built into continuous integration pipelines, and you can set up automated alerts when, for example, certain OSS licenses appear, or when a certain degree of security risk is seen, or when new components arrive that you weren't expecting, those kind of events. My next principle is that both general and specific concerns matter. There are many security concerns that transcend individual bits of technology, and that's often where people focus. Things like SQL injection attacks, very important to understand, and absolutely something that applies in almost any environment where you've got a database. On the other hand, we've also got to remember that individual technical stacks have specific weaknesses. C and C++ have major security weaknesses in their memory management. Java's got reflection and serialization, both of which are big possible security concerns. Python's got module loading, again, a big possible security concern, and there's a bit of overlap between those actually. So this principle is just not to focus on either just your technical stack minutiae or the generalities. Unfortunately, we need to consider both of them. So if we can apply those principles, I believe that your software security is incrementally going to keep on getting better. And once you've applied these principles for a while, do start thinking about how you improve your secure design. Also start talking to your infrastructure colleagues and thinking about operation. When you want to start improving your practical activity, your practical security practice in a particular code line, people often start with secure coding guidelines, and that's not a bad place to start at all. There are a number of them to be aware of. Do you remember I mentioned SafeCode? They produce a set of secure coding practices for different languages. They're very practical, and they're based on lots of real-world experience. And similarly, I mentioned OWASP, the volunteer organization that produces terrific resources in software security. They've also got secure coding practice guidelines for many common languages. But I'll also mention the common weaknesses enumeration. You may well have come across this. It's a free product and service of the MITRE Corporation in the USA, and they track common weaknesses that are found in software throughout the industry. And the CWE is a very useful aide-memoire of the kind of things that we all get wrong in security development all the time, so that we think about how we eliminate those in our particular environment. Because the problem with the generic guys, of course, is they know nothing about your specific environment. There are quite a few published guidelines. A few of them I pull out here. There are the CERT guidelines, the organization I mentioned in the USA. CERT, who are affiliated with the Software Engineering Institute at Carnegie Mellon. They've got one for C and they've got one for Java. There's also an SEI book on secure coding in C and C++. A lot of US DoD contractors have a strong interest in C and C++, so the SEI has spent a lot of time working on coding guidelines for it. And they produced one for Java. There are less guidelines for Python, though Python is very, very common today in our software. But there is a relatively new book. Dennis Byrne is just finishing it, actually, for Manning. I've seen the early cut of it. He hasn't quite finished it. I've seen the early cut, the MEEP, as Manning called them. And it's a pretty thorough book, very focused on Python specifics. If I had one criticism of it, I'd suggest he probably needs a bit more of the generic guidelines up front, but there's a lot of tremendously valuable information specialized for Python developers in that book. And then lastly, of course, the platform vendors themselves. Oracle in the case of Java, Microsoft in the case of .NET have secure coding guidelines. There are quite a few of these guidelines, as you can see, and they overlap significantly, but they are different. My warning about them is that they take time to understand and apply. Just the Oracle Java guidelines have 71 guidelines. I think it's quite clear that most people are not going to hold that in their head the whole time. I would suggest this is a great first task for your security champions to work on. Pick the security and coding guidelines that are relevant to your environment, and then work out how to apply them in your environment. Which are the most important? How are you going to train people? How are you going to check that people are managing to follow them? And it's something that allows the security champions to really gel and to think out what's important in your environment. An example of a generic attack, of course, is SQL injection. That's one I'm sure you're very familiar with, where if you have a parameter passed into an SQL statement and you don't check what's in that, somebody can subvert the meaning of the query. But there are these, as I say, language-specific examples. The SQL injection attack applies to nearly all stacks. To just give you one example from the Java world, Java's got 2 random number generators. Unfortunately, quite a lot of people don't know that. It's got Java util.random, that's not really random, but is really quick. And there's java.security.secureRandom, which is truly random, but not very quick. Guess which one people tend to use? Java.util.random, which is a pseudo-random number generator, which from a security perspective can be disastrous because we often rely on random numbers for part of our security mechanisms. So that's just one thing from the Java world, very specific to Java. And Python, something very specific to Python, pickling. Pickling is Python's serialization system. To be fair, Java and C# have similar mechanisms. It's a really useful way of moving data around and a total security liability. To be fair to the Python community, it's very clearly stated in the docs, pickle isn't secure. Make sure you trust the data before unpickling it. Sound advice, but not advice I found that people always understand or always bear in mind when using pickle. So that's another example of a very stack-specific thing to think about. So I'm just comparing and contrasting. There are some generic things we all need to worry about, but in your individual stacks, be you Java, be you C#, be you Python, whatever, be you JavaScript, there are specific things we need to know. Finally, security testing and validation. As I've said, unfortunately, I just don't have time to cover it in this talk. It would be a really interesting talk by itself, I think. But like any other critical system quality, it needs to be tested early and continuously and not batched up at the end, which is often where security testing is considered these days. Things are getting better. I think security testing always used to be at the end, and now it's starting to move earlier, but it's something you still see a tendency to think about security testing very late. As I've said, there's automated security testing tools, making sure as well that you've got functional testing of security features. How about your authorization system? Exploratory testing, things like penetration testing, and platform testing, making sure that the platforms we're running on are secure. And there are some tools emerging, particularly on cloud platforms, that can check your cloud platform for common security problems. All of these things are important in security testing. So we need to integrate this into our life cycle too. So in summary, a lot of the technology we use is inherently insecure, and that's just the way it is. I always joke that if I wanted to create a perfect attack platform, I'd probably design a web browser. So mitigation needs to be part of our application development. As we saw, attacking systems is becoming industrialized. It's becoming something that almost anyone can do by spending a fraction of a few Bitcoin. And digital transformation is providing people with ever more valuable targets to go after. And as we can see from that data breaches report, it is really happening. So secure implementation is part of the end-to-end approach to help mitigate this problem. There's 3 main aspects to secure implementation. How are you going to go about building the software? What is your SDLC? And how are you going to integrate security practice into it? Practically, What are you going to do? What practices are you going to follow when you're building the software? And principles are a good way to guide people to be thinking about how they're changing their behavior, what practices they should be using. And guidelines are very specific, both generic guidelines from people like OWASP and very language-specific guidelines, like the ones we saw earlier from people like CERT, Oracle, and Microsoft. They've both got their place. Principles are more general and guide people towards the right behaviors and the right decisions. Guidelines are very specific, sort of tell people what to do. And we really need to have both. And then the question is, once you think you're building software in a more secure manner, how do you verify what you build? And that's testing and validation, which we've not been able to talk very much about. We then explored a set of principles. Security is everyone's concern. Make sure we focus on security right through the life cycle. It's not something we put at the end. Do good design. Good design's got all kinds of benefits, and one of those benefits is it can often improve security. Use proven tools and technologies. Don't always use the most bleeding edge thing. Make sure that something has been out for long enough that the vulnerabilities have been found, and make sure that we're tracking vulnerabilities and using versions that are as secure as they can be. Automate security checking whenever we can, but be aware of the limitations of security checking. We use a lot of third-party code in our systems today, so verify the software supply chain. And bear in mind that often people focus on either generic or technology-specific concerns. Unfortunately, we need to be aware of both. SQL injection attacks, configuration problems happen everywhere, but we need to address them. On the other hand, every language has its particular pitfalls, and depending on what technologies we're using, we need to be aware of those too. We haven't really explored security testing and validation, as I've said, but it's an important area to learn about, maybe something to work with your test teams and encourage them to go and learn more about how testing can be integrated into the lifecycle for security in just the same way that it often is for things like performance. There's a number of books that I think are worth exploring. I can't take you through all of them now, but a few to just pick out are Secure by Design is a very good explanation of that, using design to drive security, as I mentioned. And Agile Application Security is a really good book on how to integrate security into the Agile lifecycle. Security Engineering is should you want to be a security engineer, I always point this one out. It's Ross Anderson's classic, now in its 3rd edition. It's the most comprehensive and actually, I think, readable book I know on in-depth security engineering. And the other one we've mentioned a couple of times is the SafeCode organization, who produce a range of publications, one of them being their Fundamental Practices Guide, which is freely available and well worth consulting as soon as you can. So what do you do? This has all been fine, but what do you do when you get back to work? Get started. Make a start. It's the first step. It's the most important one. Work out where you are. Maybe think about mapping yourself against one of those models. Get some people interested. They're the people who will become your security champions. Work out what the next thing to improve is. Don't try and improve everything at once. Start with something specific and improve that thing. And once you've improved that thing, go back and work out where you are. Get some people interested in improvement and work out the next thing. And just continue. Before you know it, you'll have greatly improved your software security. Thank you for your time. I've enjoyed talking to you.